Welcome back to Mechanics and Control of Robotic Manipulator. The last lecture we have seen introduction to inverse kinematics. Mainly we have seen what are the methods of solutions and what are the way we can actually like start approach, but we did not see yet to see any example, right. So this particular lecture is going to talk about what you call you can say finding a closed form solutions. You have seen one such method of solution is closed form. In that sense, it will give the analytical relation between one to another. So we will try to see few example and then see whether we can derive the closed form solution. So as long if the system is in planar, so 3 joints, so 3 equations we can find it. So however, if you go for you can say multi-body, in the sense if it is go for a spatial system, then we have to see the necessary and sufficient condition. The necessary condition is actually like you can see that given point supposed to be within the workspace, and there are supposed to be 6 joint. In addition to that, the sufficient condition is, or you can say the necessary and sufficient condition, one is the workspace, the other one is 3 you can say consecutive rotary axes supposed to be parallel or intersect at a point. So these all we have seen. So now this particular lecture what we are bounded, so we are bounded to see some example related to inverse kinematics. I have taken 3 such example, we will see so how the things goes. So for that what we are trying to take, first thing we are taking as a polar manipulator, which means it is a rotary and prismatic planar parallel manipulator, planar serial manipulator. Okay. So in the sense why it is called polar, because it is giving the polar coordinate. Okay. Polar coordinate is r and theta, right. So that kind of thing it is going to give, that is why it is called polar manipulator. So in this sense it is in a planar case where you want to actually like get xy translations. So it can be obtained by changing, you call theta 1 and d2. Okay. So this is the main benefit. So now this frame of you can say reference, we can actually like take it xb and yb which is given. So what we can see, we have to construct the frame arrangement for this given RP manipulator. So there are several way. So two of the way which is actually like normally people uses. So one way is actually like we can start with the base, we can start with the first joint which is Z1, which is having a rotation which is called theta 1, and the second which is actually like translation, which you can actually like write it. So in the sense, so theta 1 d2 can be written this way. So this is going to give a very much benefit. What benefit? So you can see like your x1, which is we write the perpendicular to the plane containing z1 and z2. So here what plane it is containing? So this is the plane containing. So your x can be come outward or inward. In this case I took it actually like outward, in the sense x1, okay, and x2 can be parallel. Further what you can see, I have a plenty of choice, in the sense my z0 also can be parallel with z1, and z3 I can choose in such a way that it is parallel to z0, in the sense I can take everything is actually like parallel, in the sense there is no alpha. So alpha 0, alpha 1, alpha 2 and alpha 3, so all are actually like zeros. Okay. Whereas the other conventional method which says you can start the z1 which is actually like giving theta 1, and z2 which is conventional, very much conventional, z2 which is d2, right. So in this case what is the plane containing? So z1 and z2, this is the plane containing, right. So in the sense this is the plane containing, your x axis supposed to come outward or inward, in the sense it is supposed to go vertically up or down. So here I am taking actually like coming out, in the sense it is going vertically upward. So now you can see like it is having some rotation is involved with x1, right. So now I am taking for my convenient, I am taking as z0 is actually like parallel. So x0 is actually like here. So now x0 to x1 there is a rotation, and z0 to z you can say 1 there is no rotation, but z1 to z2 there is a rotation, in the sense alpha you can say 1 there is a exist. Okay. So in the sense there is a exist in alpha 1, and you can actually like take it z3 parallel to z0. So then you can see like you can actually take it x2 like this and x3 like this. In the sense again you can see like a Z2 to Z3 there is another. So, in the sense alpha 2. So, in the sense alpha 1 and alpha 2 is actually like coming into a picture, right. So, which is non-zero, where in this case these all are actually like 0. Further, if you want to think about your forward kinematics, I assume that this is the point P, the Px what you can expect from here, because this is 0 degree, right. So, in the sense what would be the Px? So, Px is actually like minus d2 sin theta 1 in this case. So, what would be Py? So, Py is actually like d2 cos theta 1, right. So, that is the case, because your y 0 is coming this way. In this case what you can see, the y 0 is actually like going upward. So, in the sense the Px would be, so d2 cos theta 2 sorry theta 1, and Py is actually like d2 sin theta 1, right. So, we can actually like get this, but this is actually like what you call forward kinematics, right. So, we will see how formally we will do this. In the sense we will take this and frame arrangement, get the DH parameter, substitute that into the arm matrices, and then you can multiply and finally get, you can start from P, you can say E with respect to base, that is coming this or not, we will check it. So, for that I am taking this representation, because even you can take this, but I am taking one such example because this is bounded for inverse kinematics. So, you can see this is the frame arrangement which I had drawn already, that is what we have taken. The theta 1 is one of the variable which is a rotary joint, which is actually like on the base, and d2 is actually like a piston cylinder kind of arrangement which is actually like sliding. So, now Z3 and Z0 are parallel, okay, and x3 and x0 also parallel. In the sense what you can expect your orientation matrix, it would be so identity matrix, right. Your rotation matrix is identity. What would your position vector? So, your position vector is actually like a d2 so cos theta 1 and d2 sin theta 1 and 0. Whether we are getting this or not, we will see. For that you can actually like write your DH parameters. So, what are the DH parameter you can write? I. So, alpha I minus 1. So, A I minus 1, okay, then theta I and di. Okay. So, here how many frames? There are 3 frames we have to bother, 1, 2, 3. So, 0 to 1, is there any angle difference, or you can say with respect to x0, is there any angle between z0 and z1? No, right. Is there any distance between z0 and z1 along x0? No. So, what is actually like about z1? Is there any angle between x0 and x1? Yes, which is 90 degree. In addition to that, what? So, the z1 is actually like active, right. So, that you can write it. So, what actually you can see along z1 there is no distance between 0th frame and 1, right. So, in the sense this distance is 0. Now, coming to the second one. So, this is actually like here. So, now you can see about x1. So, there is a z1 and z2, there is a distance which is positive because it is rotate like this, this is the rotation direction. So, in the sense it is actually like z1 to z2 is positive, in the sense pi by 2 positive, and there is no distance along x1. So, 0, and you can see x1 and x2 parallel, and about z2 there is no angle. So, that is 0, and what you can see there is a distance along, you can say 1 and 2 frame. So, that is what I call d2, right. So, in this case this is variable and this is variable, right. So, now what else? So, the third frame is actually like the displacement is nothing because 2 and 3 are coincide. So, you can actually like directly put that 0, but what you can see about x2, the z2 is actually like rotate 270 degree to make coincide, in the sense 3 pi by 2, right, and theta also there is an angle with respect to d3 sorry z3, you can see that there is an angle, right. So, then you can see that is pi by 2, right, but here actually like what, this is the rotation, right, in the sense it is actually like z x about z3 x2 to x3 distance angle, that is 3 pi by 2, right. So, now this is a DH parameter, which is we obtain, right. So you can actually like see which we have obtained. So now what you can actually like see, whatever we have written, that all coming into a picture, right. So in the sense, this is the variable and this is the variable. We can substitute this into individual arm matrices, and then we can see what is you can call the DH representation giving finally forward kinematics, right. So that we can substitute and finally multiply. You can see this is the final multiplied the matrix, what you get. So you can see that this is the position vector which we have written, and this is the you call the orientation or the rotation matrix. So in the freezing point, theta 1 is actually like 0 degree. So if you put 0 degree, what it is giving? So it is giving d2 0 0, that is what x displacement only there, right. So you can actually like recall. So this is 1 and 2, this is d2, and this is 0 also, this is okay. So in this case you can see this displacement along x, so d2 is coming, so you are actually like getting it. And if you substitute this, this become 1 0 0, this is 0 1 0, and 0 0 1 is. So in this case you can see it is identity matrix, that is also matching, right. So now what one can actually like find it. So you can actually like see this is the you can say position vector. Since it is a 2D of system, so we can actually like see only two variable can be task space. So here the task space variable is only x and y. So that is what we call px py. So in this sense, mu here is only px py. Okay. So this is the task space vector that I can write as function of q. So q is actually like vector here. So theta 1 and d2. Okay. So now what that? So you can write mu as, okay, so d2 cos theta 1 and d2 sin theta 1. So this is what you call forward kinematics. You got it. Now if I actually like give px and py, can I find theta 1 and d2? Yes. In this case it is straightforward. You square and add, what it will come? It will give only d2 squared. So you can take it that square root. So that would be your d2, and you take p y divided by px, that would give tan theta 1, right. So that is what we are saying. This is the forward kinematics for given PR manipulator. So if you actually like take this py by px, so that gives actually like what it is equivalent. So d2 sin theta 2, sorry, theta 1 divided by d2 cos theta 1. So which case this get cancelled, this is giving tan theta 1. So in the sense, so theta 1 is tan inverse of, so py by px, and what we say, it is actually like quadrant dependent. So you take theta 1 as, so a tan, in the sense arc tan, two argument py px, in the sense the sign of px and py makes sense. Okay. So now the square and add, so that will give d2. So square and add means what? So px squared equal to, so d2 squared cos theta 1 squared. So py squared is d2 squared sine, so theta 1 squared. So if you actually like these two add, what it will come? Px squared plus py squared equal to d2 squared. So from there you can get this relation, right. So now you can see this will give plus or minus. So it is giving a multiple solution, but this multiple solution is actually like not really possible. Why? Because it is actually like only positive, because the d2 have restriction, right. So this is lower limit and this is the upper limit. So in the sense it can be equal, but in that case the positive value only will come. That's why I did not put plus or minus. Okay. So now this is one such example which is very easy. We'll take one another example. What another example? You still in planar, but you have it, you can say three rotary joints. So this is one rotary and this is second rotary and this is third rotary, where theta 1, theta 2, theta 3 are the joint variable. In the sense your q vector would be theta 1, theta 2 and theta 3. So in this case the mu vector, so is, it's in a plane. So x translation, y translation, and you can say z orientation, right. in the sense the P xy and the angle with respect to x axis of 0 to nth axis, that is what you call psi, right. So, now what you can see, the mu can be written as function of q. So, this is what you call forward kinematics. If I give mu, can I actually like find q, right. So, what that? So, F inverse of, you can say this as mu. So, this can be found. This is what you call inverse kinematics. So, for that what first one supposed to do? We have to fix the frame arrangement. So, since it is a planar, what you can do? You can actually like start the Z1, okay. You can do it either way. So, I can say this is Z2 and this actually like a Z3, okay. So, then even I can actually like extend that, I can put as Z4. In the sense this will be L1, this is L2 and this is L3, and even I put it Z0 also common, then it will go X1, this goes X2 and this goes actually like X3 and this goes X4, right. Like that I can actually draw, and then I can find this this distances and all coming, and here theta 1, this is actually like theta 2 and this is theta 3, like that I can fix a frame, right. So, for benefit I just drawn that with some angle. You can see like this is the, you can say Z0 and Z1, where this is the frame 0 and 1, this is the frame 2, frame 3 and frame 4, where you can see the each x axis aligned with the link, and in the sense along this length you got link length L1, L2 and L3, and the angle between x0 and x1 about Z1 is theta 1, then angle between x1 and x2 is theta 2, x3 and x2 is theta 3, and finally this angle called psi, okay. So, now this position is x and y. So, now can we do it? Yes, it is straightforward. So, x I can write L1 C1 means cos theta 1. So, L2 C1 2 means, so cos theta 1 plus theta 2. So, this is L3 C1 2 3 means cos theta 1 plus theta 2 plus theta 3. So, the y is L1 S1 plus L2 S1 2 plus L3 S1 2 3. So, in this case we really do not require the DH parameter, but still we can do it. Then the psi is theta 1 plus theta 2 plus theta 3. So, what this? So, this is actually like related to mu. What is this? This is function of q, right. So, in the sense forward kinematics we have done, right. So, what we need? We need, if I give x, y and psi, can I find theta 1, theta 2 and theta 3? Can I find it? Yes, we can do. So, for that we will actually like do the DH parameter, we will get this transformation matrices, and then we will actually see this is the position vector, right, and this is the orientation, right, we got it. So, now even you cross check, you put all thetas as 0. So, what you will get? So, in x axis L1 plus L2 plus L3, in y 0 and z obviously 0 because it is in a planar, and if that is the case, so Z4 and Z you can say 0 are parallel. In that sense you can see it is supposed to be identity, that is also getting it, right. So, this is 0 0, right. So, we are not bothering about the frame arrangement, or we are not bothering about the position vector. What we are bothering about, if I give the position vector and orientational information, can I find theta 1, theta 2, theta 3 individually. So, for that what one can see, so we can rewrite this equation, and again I write. So, 1 2 means theta 1 plus 2, 1 2 3 means theta 1 plus theta 2 plus theta 3. So, now what you have? So, you have this equation, right. So, what equation? X1 and X2, in the sense you have x, so L1 C1 plus L2 C1 2 plus L3 C1 2 3. So, y is L1 S1 plus L2 S1 2 plus L3 S1 2 3, right. So, in the sense what you have? You have this, and psi is, so theta 1 plus theta 2 plus theta 3. So, this relation you have. So, what one we are actually like expecting? So, based on this, these are given, in the sense I am marking in green color. So, these are given, can I find, so this, okay, in the sense can I find this? So how I can do? You can see there are several ways. So one is, if it is psi is given, what one can see from this point, so you can actually like come back this point. What that mean? So if you write P1, so P1 is actually like where you call x1 and y1. So that can be written as what you can write. So it can be written as, so L1 C1 plus L2 C12, right? Because that is the point, right? So that can be equal to what? So you have this distance, you subtract this. So in the sense, so you can actually like see that this Px, or you can write as, so you can write as x minus L3, so cos psi will give this, right? Similarly, L1 S1, in the sense this vector is equivalent to from this, right? In the sense I can actually like go this vector addition, or I can go this way, right? Both are actually like representing this. So in that sense I can write x1 and y1 in this form. So now what benefit I will get? So the C phi and S phi are known, and L1, L2, L3 are geometric parameter which are again already known, and x, y are known. So what you can see, this I can equate as, so L1 C1 plus L2 C12, this equate to L1 S1 plus L2 C12. What I can do, I can square and add. So what you can see, these two equation will give one equation, but that equation will give only theta 2 as a function, right? So what I can see, I can get it, right? So that is what I am actually like trying to see. So what that mean? So I am actually like squaring and adding means what I can see, I am taking this as this length. So now you can see that is what actually like trying to find, and that to further simplify, I will get this theta 2. Okay. Once I get this, then I will actually like come back to theta 1. How? That I will show you. So right now this two are equal. Okay. I am rewriting into my own benefit. So now I am squaring and adding. So this x1 squared, y1 squared, which is I am actually like adding. So this would be equal, and this. So now what I will get? So this is the final equation, right? So now here I substitute x minus L3 cos phi whole squared. This I can actually like y minus L3 sin psi whole squared, I can substitute. Then you can see the left hand side is known. So what is unknown? Only this cos theta 2. If I find cos theta 2, okay, I can easily find sin theta 2. What that? It is actually like square root of, so 1 minus cos, so cos theta 2 squared, right? Because we know sin theta squared plus cos theta 2 squared equal to 1. So based on that I can find this. So once I know sin theta 2 and cos theta 2, what I can do? I can take tan theta 2, right? So then I can write theta 2 as a tan 2 as like this. I put S2 is sin theta 2, C2 is cos theta 2. So like that I can actually like mark it, right? So in the sense what you can actually like see, so the theta 2 I can get it. So once I get theta 2, what I can do, that I will show you, okay? So what you can actually like look at it. So now you can actually like see here in this particular slide, we have taken cos theta 2 from this big equation. So this equation we modified, and we have found the sin theta 2, then we have found the theta 2. Once this is known, you come back to this picture. What is known? So this L2 is known, and this theta 2 is known. So what one can see, this triangle we can make it, right? So what that? So this theta 2 is known, this I can mark it as L2 cos theta 2, and this L2 sin theta 2. But what is this distance? It is a link length L1, right? So this is L1. So now this total length, what I can get? I can make this triangle, right? So then what I can see, I can find some angle called beta, okay? So in the sense, so I can see, so this is actually like L2 sin theta 2, and this is L1 plus, so L2 cos theta 2, Okay, this angle I call beta. Okay. Further, what I know, this point is actually like P1, right? The same P1 I can actually like mark it like this triangle. So what that? So this P1 and I mark it this. So what that? So this is actually like x1 comma y1, right? So this is y1 and this is x1, and this angle I can call alpha. Okay. So now you can actually like superimpose these triangle. What you can see that the theta 1 is actually like something is coming, sorry, right, this is the superimpose. So now this angle is beta, so this is actually like theta 1. So for that, what one can actually like do it, so we can actually like use the relation which we have. Okay. So what we can see, this is all already known. So the beta I can find as tan, so tan inverse of what, so L2 sin theta 2, so divide by L1 plus L2 cos theta 2. So what is alpha? Alpha is tan inverse of, so y1 divided by x1. What is theta 1? Theta 1 is alpha minus beta. So this relation I am bringing it now. Okay. So you can see that alpha is actually like tan inverse of y1 divided by x1, and beta I am writing as this form. So now what is theta 1? So theta 1 is actually like alpha minus beta. But what is you have written psi? Psi is theta 1 plus theta 2 plus theta 3. Already I know this. So what is theta 3? So psi minus theta 1 minus theta 2, right? So you get all unknowns for given x, y and psi, right? So now you got what you call in inverse kinematics. In the sense you found theta 1, theta 2, theta 3 from the help of x, y and psi, right? You can see this same thing you can solve it in number of ways. So I have shown one simple way, but there is no unique way. This is the only procedure you have to follow. Even you can go with the numerical solution, all those things, right? So now I have just to give only one slide further, which is actually like self-explanatory. So you can see that the spherical robot, we have already, you can say, draw the frame arrangement, and we have found the DH parameter. And what we got, so we got finally based on the final transformation matrix of 4 with respect to 0, right. So in this case the T3 with respect to 0 will give rotational information of 3 with respect to 0 and positional information of 3 with respect to 0. So these all we have seen, right. So now since it is actually like 3D of system and it is going to give a major axis, because we have seen that transformation matrix of 7 with respect to 0, we can actually like simplify it as 0 to 3, and we can say that 3 to 6 and 6 to 7. This we call tool, okay, tool orientation vector or matrix, and this is actually like minor axis transformation, and this is actually like major axis. What that mean? So your wrist need to be positioned on the space, so you need 3 coordinate transformations, right. So you need to have a this particle position, you need to have it, in the sense you need to have x, y, z. So this is major. So that's why the first 3 joints we call major axis. So the next 3 joints is actually like orient your wrist, so we call minor axis. The last, you can say, final axis, which is just a tool orientation if it is a 6D of robotic manipulator. If it is actually like other than that 6, if it is actually like 7 or 8, so then these 2 axes we call redundant axis. Okay. So now you are clear in that. So based on that, the spherical robot, what it is giving? It is giving 3 axes. These 3 axes called major axis. So based on that, you can see this is corresponding to x, y and z. So in the sense what we are interested, the position of the end effector is what you call forward kinematics. So in the sense x, y, z can be obtained. So this is we have done already with the previous lecture. So now based on this, if x, y and z as given, can I find theta 1, theta 2 and d3 in this case? Yes, we can do it. So for that, what one can do? So you can see here, so the theta 1 is actually like common, right. And if I divide, So y divided by x, what it is giving? So this d3 will go and sin theta 2 will go. So what it gives? Sin theta 1 divided by cos theta 1, in the sense it is giving tan theta 1, right? So in the sense what you can see, so if you take tan inverse of y by x, that will give theta 1. So for theta 2, what one can do? So you can actually like do it this way. So z minus d1 is giving d3 cos theta 2, and the other way around you can see x divided by, you can say x divided by cos theta 1 is d3 sin theta 2, right? So now you divide by x divided by cos theta 1 divided by z minus d1, what it will give? It will give tan theta 2, right? So that way we can actually like calculate, right? So here I have taken y divided by sin theta 1, anything you can take. So now, so this we have taken because this theta 1 negative sign will play. If you have theta 1 is actually like a negative value, if you take cos theta 1, that will not give the sign change. So that's why we have taken sin theta 1. Okay. So now what would be the d3 you need to have? So d3 can be calculated in number of way. So one of the way you can actually like square and add these two. So that would be like what you have done here. So you can actually like take y divided by sin theta 1. So that is actually like equal to, so d3 I think d3 sin theta 2, and z minus d1 would give d3 cos theta 2. So you square and add, so then you take a square root, this is what coming. So now we can see like if you have a forward kinematic solution and you have actually like number of unknowns equal to number of equation, you can solve it. So the next lecture would be on numerical you can say method. So how to get the inverse kinematics through numerical method. One of the popular method we are going to call as in, you can say Newton-Raphson method, we will be taking it. So with that, this particular lecture is ending. See you then in the next lecture. Thank you.